the deep dive. Today, we're opening a book that, well, you've probably never actually picked up. It looks, frankly, more like an old engineering manual, just pages and pages of numbers.
Yeah, it's pretty dense looking.
Exactly. But this book, Tables of the Riemann zeta function, published way back in 1960 by Hazelgrove and Miller, it fundamentally changed things in mathematics.
Oh, absolutely. It's one of those sources that's, indispensable in the field, but the real story isn't just the numbers themselves, it's what they represent.
Right.
This collection of, well, cold, hard data, it marks this singular moment, a real turning point in both human intellectual history and technological history.
And the introduction to the book, which you mentioned, is maybe the most valuable part for us looking back.
Definitely. It lays bare the sheer effort involved, the monumental task it was back then to achieve something computationally that honestly we barely think twice about today. This book is, it's easily one of the most important yet probably least read books in the whole mathematical library.
That introduction really does capture the imagination. So our mission today, for you listening, is to understand how this incredibly dry-looking volume, these tables, signal that definitive shift. The moment math moved from just pen, paper, and brain power
Painstaking hand calculation.
to being powered by these brand new, pioneering electronic computers. This isn't just a data set, is it? It's more like the official birth certificate of computational number theory.
That's a great way to put it. Precisely right. We're going to try and extract the critical knowledge from these tables, sure, but maybe more importantly from that technical introduction. It details how they were made.
And the whole thing, the whole reason for this massive undertaking, it all comes back to one thing, right?
The Riemann hypothesis, yeah.
Yeah.
Arguably the biggest unsolved puzzle in all of mathematics. This book, this incredible effort, it was all evidence gathering, a direct assault on understanding that hypothesis.
Okay, so let's lay that groundwork really quickly. Before we dive into the computers and the calculations, why this function?
Hmm.
Why the Riemann zeta function? Why did it demand this, frankly, heroic early computational effort?
Well, the zeta function is absolutely central to number theory. It's like a Rosetta Stone, connecting the world of continuous mathematics calculus and complex analysis to the discrete, messy world of prime numbers.
These primes, right? Those numbers that seem random but must have some pattern.
Exactly. And the zeta function holds the key somehow. The authors, Hazelgrove and Miller, they zoomed in specifically on its behavior along what's called the critical line. It's this very narrow region where the function's most mysterious, most important behavior happens. Behavior that directly dictates how those prime numbers are scattered.
So the goal wasn't just, abstract curiosity. It was highly strategic.
Oh, completely. The ultimate purpose was twofold. One, rigorously test the Riemann hypothesis by mapping out exactly where the function equals zero, its zeros.
Yeah.
Two, provide the most dependable, verified numerical data possible for anyone else working on primes. Before this, people were working with much patchier, less reliable data.
A strategically vital data dump, essentially.
That's it. Designed to kickstart research, provide solid empirical footing, and maybe, just maybe, offer strong evidence for the truth of the Riemann hypothesis itself. It was really the first time mathematicians had this kind of high-precision, computer-verified data on the zeta function's core behavior.
Okay, let's get into the function itself then. It's the main character here. Conceptually, what is the zeta function at its most basic level?
So conceptually, it starts out surprisingly simple. The zeta function, usually written as a zeta, that's the Greek letter zeta, it's defined as an infinite series, an endless sum. Imagine adding up fractions. 1 over 1 to the power of z, plus 1 over 2 to the power of z, plus 1 over 3 to the power of z, and so on, forever. And that z isn't just a number, it's a complex number. It has a real part and an imaginary part.
Right, and that's where the first big hurdle comes in, isn't it? And why they eventually needed computers. That simple-looking sum, it doesn't always work.
Exactly. That infinite series definition only converges, meaning it adds up to a sensible, finite value for certain values of z, specifically only when the real part of z is strictly greater than 1.
And if the real part is 1 or less than 1,
it blows up.
Yeah.
The sum diverges, goes off to infinity. It just doesn't give you an answer, which is a problem because the really interesting stuff, the connection to primes, happens precisely in that region where the simple sum breaks down.
So you can't just use the simple definition to study the most important part.
Correct. So if you want to understand the whole picture, especially how primes work, you need to know what the zeta function is doing everywhere, even where that basic sum fails. And this requires this profound mathematical idea called analytic continuation.
Okay, that sounds pretty technical. How can we think about analytic continuation? What's the core idea?
It's like finding a loophole, a clever workaround. Mathematicians figured out how to transform the original formula algebraically into a new expression. This new expression gives you the exact same answers as the original sum wherever that sum worked.
Okay, so it matches up where it should.
Right. But crucially, this new expression also gives you a consistent, mathematically valid value for z everywhere else, even where the original sum diverged. It's like extending the function's domain, its territory, across the entire complex plane, finding a sort of master formula that captures the essence of the original, but without its limitations.
And once you've done that, once you've extended it, you uncover this really neat property, right? This mirror thing, the functional equation.
Yes. The functional equation is absolutely fundamental. It's beautiful, really. It reveals this deep symmetry. It shows that the value of the zeta function at some complex number z is directly related in a predictable way to its value at 1 minus z.
So like reflecting across the point z equals 1/2.
Exactly. It creates this mirror symmetry around the critical line where the real part is 12. If you understand what the function's doing on one side of that line, you automatically know a lot about what it's doing on the other side. It helps organize the whole investigation enormously.
Okay, so we have this function defined everywhere now, thanks to analytic continuation, with this nice symmetry. And the big prize is finding its zeros. The point z, where the function's value is exactly 0. Why are those the magic numbers?
Because somehow, encoded within the precise locations of those zeros is the secret to the primes. That's Riemann's great insight. But we need to be specific. As the introduction points out, there are two types of zeros.
Right, the easy ones and the hard ones.
Pretty much. There are the trivial zeros. They're predictable, easy to find. They just sit there on the negative real axis at all the negative even integers. -2, -4, -6, and so on forever. They're trivial. They don't tell us much about the primes.
But the non-trivial zeros, those are the ones that matter, the ones that hold the secrets. And they all seem to live in this specific neighborhood on the complex map.
They do. All the known non-trivial zeros, and we think all of them period, reside within what's called the critical strip. This is the zone everyone cares about. It's the infinite vertical strip in the complex plane where the real part of z is strictly between 0 and 1. That narrow band is ground zero for number theory's biggest questions.
And inside that strip is where the Riemann hypothesis makes its incredibly bold claim.
Incredibly bold, yeah. The Riemann hypothesis, or RH, asserts something remarkably simple yet profound. Every single one of those non-trivial zeros doesn't just lie somewhere in that critical strip. It lies exactly on the line running down the middle of it.
The line where the real part is precisely 1/2?
Precisely 1/2. That's the critical line. If the RH is true, it means the seemingly chaotic distribution of prime numbers is ultimately governed by this perfect hidden order dictated by zeros lying perfectly on this single line. That's why it's such a huge deal, with connections to physics, cryptography, $1 million prize problem even.
Okay, now connect this back to Hazelgrove and Miller in the late 1950s.
Yeah.
They want to test this. They want to find these zeros on the critical line.
Yeah.
But calculating the full zeta function, zeta, with its complex numbers, on those early, clunky computers, that sounds like a nightmare.
Oh, it would have been practically impossible with the required precision. Numerical stability would have been a huge issue. They needed a smarter way, a computational shortcut.
And that's where this other function, ZT, comes in. The foreword really highlights this as the practical tool.
Exactly. ZT was the crucial simplification. Instead of wrestling with the complex valued zeta directly on the critical line, they focused on this related function, ZT. It's a purely real-valued function, no imaginary parts to worry about, and it's cleverly constructed so that its behavior perfectly mirrors the zeta function only along that critical line.
And its behavior is simpler, easier for a computer to handle.
Much simpler. ZT just oscillates up and down like a wave along the real number line as t increases. Think of a sine wave, though much more complicated. It goes positive, negative, positive, negative.
Which is way easier for those early digital machines to track than complex numbers.
Absolutely. And here's the genius insight that made the whole project feasible. ZT acts as a perfect proxy. Every single time the value of ZT crosses 0, passes through the x-axis, going from positive to negative or vice versa, that exact point t corresponds perfectly to a non-trivial 0 of the original zeta function, lying precisely on the critical line.
Ah, so you don't need to calculate z at all. You just need to find where this real valued wave, ZT, hits 0.
That's it. Find the 0 crossings of z. And that's what this book fundamentally is. A massive, high-precision, meticulously verified list of those zero crossings. It's the raw data, the empirical evidence testing the Riemann hypothesis, far, far beyond what any human could calculate by hand before.
Okay, the mathematical setup makes sense. Find the zeros of Z. But now we hit the wall of 1950s technology, achieving the necessary precision, let alone on those first-generation electronic computers. This wasn't just running a program. This sounds like a serious engineering feat.
Oh, the difficulty is hard to even imagine today. We're talking about the real pioneers of computing hardware. The book mentions the specific machines. The EDSEC, that's the Electronic Delay Storage Automatic Calculator at Cambridge University.
Legendary machine.
Truly. And also the Manchester Mark I. These weren't sleek desktops. They were behemoths. Room-sized constructions filled with vacuum tubes, notoriously unreliable, prone to overheating. Powerful for their era, yes, but incredibly demanding and unforgiving.
And Miller's preface gives this really vivid sense of the human cost of working with them. He talks about how one tiny slip-up in the programming.
Yeah, he mentions things like forgetting to handle numerical rounding correctly, or a slight logic error in a loop. A single bug like that could completely trash the results. It could invalidate weeks of continuous computation, weeks of expensive machine time, just gone.
Weeks. You just feel the stress.
Absolutely. And this unavoidable fragility meant they had to build in layers upon layers of checks. Redundancy was non-negotiable. The introduction makes it clear. Because the hardware itself couldn't be fully trusted, they had to approach the whole process with, well, almost military discipline.
Repeating calculations.
Many calculations had to be run multiple times, sometimes on different machines, just to see if they got the same answer. They weren't just using computers, they were actively validating the very idea that computers could produce trustworthy mathematical results. They had to prove the machine's output wasn't just electronic noise.
And the calculation itself wasn't straightforward. They couldn't just use one single formula for Z for all values of D, could they?
No, and that added another layer of complexity to the programming. This is a key technical point, they explain. They needed two main computational recipes, as they called them.
Recipes, I like that.
For relatively small values of 2, they used what's called the asymptotic series. It's a type of infinite sum that gets more accurate the more terms you include, and it works pretty well when at isn't too big.
But pretty well isn't good enough for this, and it breaks down eventually.
Right. As D gets larger, the asymptotic series either becomes computationally too slow, you need too many terms, or it just stops being accurate enough. It diverges. So for the bulk of the work, for finding zeros way out at large, they had to switch horses midstream.
To the much more complicated formula.
To the Riemann-Siegel formula, yes. This is a beast. A highly sophisticated, very complex formula specifically derived by Siegel, building on Riemann's work just for calculating the zeta function accurately for large arguments, especially on the critical line.
So programming that and making sure the switch between the two formulas didn't introduce errors.
Required, as they put it, extraordinary care. Just managing that transition smoothly was a major challenge. And on top of that, both formulas required incredibly precise input values. The calculations demanded, and this number is staggering for the time, 15 decimal place precision for constants like logarithms.
15 decimal places. In 1958, using vacuum tubes. We have to stop and really appreciate that. Why did they need that much precision? Couldn't they get away with, say, 8?
It boils down to the nature of calculating oscillating functions over long ranges. ZT wiggles back and forth. Tiny, tiny errors in your starting constants like log pi or coefficients in the Riemann-Siegel formula, they don't just add up, they get magnified, sometimes exponentially, as t increases.
Like a butterfly effect.
Kind of, yeah. An error in the 8th decimal place might seem tiny, but by the time you're calculating z out at t equals, say, 100,000, that tiny initial error could mean your final calculated value is completely wrong. Your zero crossing could be way off. 15 places wasn't obsessive. It was the bare minimum needed to ensure the results were mathematically meaningful and reliable out to the ranges they were exploring. It was about mathematical honesty.
Okay, so extraordinary care in programming, extreme precision in constants, and then the verification.
Yeah.
They didn't just trust their own code on one machine.
Not a chance. They had this multi-layered verification protocol that was really state-of-the-art for the time. Layer 1, do the primary computation on the EDSC.
Okay.
Layer 2, cross-check the results on a completely different machine, the Manchester Mark I. The explicit goal here, they state, was to ensure that any cumulative errors were smaller than 1 unit in the 5th or 6th decimal place of the final Z values. This was a check against potential hardware glitches specific to EDSC.
Machine versus machine. Smart. And then the final layer, the ultimate sanity check.
The gold standard. Miller makes a point of emphasizing this. Every single result, especially the locations of the zeros, had to be verified using a completely independent mathematical method provided by another giant of early computational number theory, D.H. Lamer.
Lamer's check.
Yeah.
So it wasn't just running the same code twice. It was a different approach altogether.
Exactly. A different algorithm, likely less efficient for bulk calculation but reliable for spot checks. This triple lock system, careful formula implementation, hardware redundancy check, and independent mathematical verification was absolutely crucial. It was how they built trust. It was how they convinced a deeply skeptical mathematical world that, yes, these new electronic brains could actually be relied upon to produce correct, publishable mathematical facts. They established trust through almost painful rigor.
And amidst all this technical detail, we shouldn't lose sight of the human element. You look at these tables of numbers, and it's easy to forget the sheer effort, the frustration.
Oh, absolutely. It wasn't just a technical challenge. It was clearly an emotional roller coaster, too. And they give us this rare, wonderful glimpse into that struggle in the closing parts of the introduction. They talk very frankly about the emotional lows after discovering serious errors.
I love that they included that.
Me too. Just imagine the scene. You've had the ED sac chugging away for maybe 2 weeks straight on a calculation. You finally get the printout, probably on paper tape or cards. You spend days meticulously proofreading the numbers, checking the sums, only to find a tiny rounding bug deep in the code that means the whole 2-week run was basically garbage.
Oh, devastating.
And back then, you couldn't just step through the code with a debugger like today. Finding that error meant intense mental effort, poring over the logic, maybe even rewiring part of the machine's plugboard programming, and then you had to restart the entire calculation. All that expensive machine time, all that effort, down the drain, starting over.
That one detail really brings home the drama, doesn't it? This book isn't just the output of a computer program. It's a testament to the incredible persistence, the meticulous proofreading, the sheer grit of Hazelgrove and Miller and their team. They were pushing right up against the absolute limit to the technology, and maybe their own endurance, too. So after all that heroic effort, the programming nightmares, the 15 decimals, the triple checks, what did they actually produce? If you were that mathematician in 1960 finally getting your hands on this book, what gold was inside?
Well, the bulk of the book, as the source material confirms, really is just that. The tables. Pages 29 through 53 are densely packed numerical data. That's the core scientific product. Meticulously printed, cross-checked, and accurate, they state, to 5 or 6 decimal places for the key quantities.
And these weren't just random numbers. They were designed as a benchmark, right? A test bed.
Exactly. The introduction suggests they saw these tables not just as answers, but as a high-quality data set that future researchers could use to test their own computational methods or theoretical ideas against.
Now, the book has several tables, but the one that really gets to the heart of the Riemann hypothesis mission is Table 3, isn't it?
Table 3 is definitely the main event. You could call it a census of the zeta function's behavior near the critical line. Its primary content is a list of the first 1,600 zeros of z.
1,600. That's a huge leap from what was known before.
A massive leap. So 1,600 values of t where z crosses 0, all verified to correspond to zeros exactly on the critical line. But crucially, it's not just the value of t. For each zero, they also list related data.
Like the slope.
Exactly. The slope of z as it crosses 0, that tells you how quickly it's crossing, which is important for more refined mathematical analysis of the zeros distribution.
And Table 3 also includes these things called gram points. What are those, and why include them?
Ah, gram points. They're fascinating, and including them gives real insight into the process of finding the zeros. So zt oscillates, right? Gram points are specific values of t where the wave, zt, is sort of expected to be near a peak or trough based on a simpler related function. They're like theoretical signposts.
Okay.
More importantly, between consecutive gram points where zt has the expected sign, there should be exactly 1 zero of zt. This is called Graham's law. It doesn't always hold, but it usually does.
So they act like brackets. They help you know where to look for the actual zero.
Precisely. The authors would calculate the gram points first. That was computationally easier. Then they knew the real zero had to lie somewhere between gram point n and gram point n plus 1, usually. This dramatically narrowed down the search interval for the much more intensive Riemann-Siegel calculation needed to pinpoint the actual zero crossing. Including the gram points in Table 3 basically shows the reader the scaffolding they used for the computation. It's more than just the answer, it's a peek at the method.
And their calculations weren't just limited to that continuous list of the first 1,600 zeros. They pushed further out, didn't they, to show their method held up?
Yes, that's where the other tables come in, particularly Table 2 and Table 4. Table 2 gives dense, continuous values of z itself, not just the zeros, over a specific early range, like between 100 and 1,000, useful for different kinds of analysis.
But Table 4 goes way higher.
Table 4 is about demonstrating confidence at scale. They didn't calculate every single zero continuously up to, say, T250,000. That would have been computationally prohibitive even for them. Instead, they did high-precision spot checks. They calculated Z and located zeros in specific, much higher ranges. The table includes values around T7,000, T17,000, T100,000, and even way out near T250,000.
Why was spot checking like that valuable? Why not just stop at 1,600?
It was a crucial test of the robustness of their entire method, especially the Riemann-Siegel formula and their handling of that 15-decimal precision. By successfully finding zeros accurately in these very distant regions, they were showing that their computational recipe didn't break down or accumulate catastrophic errors when T became enormous. It was like stress testing their engine. If it worked reliably way out there, you could have much more confidence in the results closer in.
Okay, so they provide this unprecedented data set. Verified, precise, covering a huge range.
Yeah.
But the book wasn't just a data dump. They also told people how to use it, right?
Absolutely. That's the real service provided by the introductory sections, especially Section 4, which is titled Interpolation. This was vital. The tables list ZD, or its zeros, at specific points, but what if a mathematician needed a very accurate value between two of the listed points?
They needed a reliable way to estimate, to fill in the gaps.
Exactly. And Hazelgrove and Miller didn't just say, go figure it out. They provided a concrete recommendation and guidance. Section 4 acts as the user manual for the tables.
And the recommended method was Lagrange interpolation.
Yes. They recommended using Lagrange interpolation. It's a standard technique where you fit a smooth polynomial curve that passes exactly through a set of known data points. You use the tabulated values near the point you're interested in to construct this curve, and then evaluate the curve at your desired point.
And they even gave advice on how many points to use.
They did. They noted it depends on where you are, the value of t, and how much accuracy you need. For smaller t, maybe using 5 nearby tabulated points in your Lagrange formula would be enough to maintain that 5 or 6 decimal accuracy. But for larger t, where the function might be oscillating more rapidly or behaving more complexly, they advised using more points, typically around 7 neighboring values, to get a reliable interpolated result. This level of practical advice shows they were really thinking about how researchers would actually work with their data.
So the tables provide the anchors, and Section 4 provides the boat to navigate between them.
That's a nice analogy, yeah. And then for anyone who wanted to not just use the data, but actually replicate the calculations or push even further, they provided the ultimate blueprint.
Section 6, the Riemann-Siegel formula itself.
Section 6 is basically the open source code for the core calculation. It lays out the full Riemann-Siegel formula they used, complete with all the necessary coefficients, the auxiliary terms, the correction factors, everything someone would need to compute z accurately for large T themselves.
Wow. So they weren't guarding their secrets. They were publishing the recipe.
Completely transparent. This was fundamental. It allowed other researchers anywhere in the world to understand exactly how the results were obtained, to verify them independently if they wished, and crucially, to build upon them. To extend the calculations to even higher zeros using the same proven methodology. This section cemented the book's role as the foundational document for computational investigation of the zeta function for decades to come.
Okay, so we've journeyed through the mathematical mystery, the incredible computational struggle, and the detailed contents of the book itself. Now let's circle back to the big why. Why do these 1,600 meticulously calculated zeros sitting on the critical line actually matter beyond just being numbers in a table? It comes back to the primes.
Always back to the primes. We have to remember Riemann's original motivation, which Section 5 of the introduction revisits. The non-trivial zeros of the zeta function aren't just mathematical curiosities. They are, in a deep sense, the fundamental frequencies that generate the pattern of prime numbers.
The introduction uses that phrase direct mirror, which is quite evocative.
It really is. It's perhaps the most profound connection in number theory. There are explicit mathematical formulas, things like the prime number theorem's refinements, and the explicit formula itself, which demonstrate that the precise locations of these non-trivial zeros on the critical line directly dictate the fluctuations in distribution of the primes.
So if you know exactly where all the zeros are,
You can, in principle, write down a formula that tells you exactly how many prime numbers there are less than any given number x, or predict where the next prime is likely to occur with astonishing accuracy. The zeros encode the precise error term in the approximation of the prime counting function. They are the correction factors that turn an estimate into, potentially, an exact count.
so for you listening, this 1960 book, these tables, they aren't just abstract data. They represent the most detailed map available at the time of the hidden structure underlying the primes. The zeros are like the architectural blueprint for the seemingly chaotic placement of prime numbers throughout the number system.
Beautifully put. And the impact of this map wasn't just theoretical, wasn't just laying groundwork for the future. This book had immediate, concrete, and quite dramatic consequences in the mathematical world almost as soon as it was published.
It wasn't just confirming things, it actually overturned something.
Yes. The sheer quality and reach of the data computed by Hazelgrove and Miller, that 15 decimal precision paying off, provided enough evidence for Hazelgrove himself to disprove a long-standing, respected mathematical conjecture.
A conjecture made by George Polya.
That's right. George Polya, very famous mathematician, had made a conjecture decades earlier about a subtle pattern in the distribution of numbers related to their prime factors specifically, about the summatory Liouville function. It essentially suggested a certain bias in how these patterns behave. People generally believed it was likely true.
And Hazelgrove used the data from this project.
He used the high-precision values of Zia and related functions, calculated out to those large values of t thanks to the EDSA and the meticulous methods, to show definitively that Polya's conjecture eventually failed. He found a point far out where the predicted bias reversed.
Wow. Just stop and think about that chain of events. The theoretical need for Xi, the wrestling with EDSC, the 15 decimal places, the triple verification, the 1600 zeros. All that intense effort didn't just add to knowledge, it actively corrected mathematical belief. It led directly to the definitive refutation of a major conjecture.
It was a massive demonstration of the power of computation in pure mathematics. It sent a clear signal. Rigorously produced computational evidence could now settle questions that had resisted purely theoretical attacks for years. It wasn't just about confirming intuition anymore. It was about discovering new, sometimes counterintuitive, mathematical truths.
So the overall takeaway from the work is this dual thing.
I think so. For the working number theorist in 1960, it was primarily an invaluable source of reliable data, a benchmark. But looking back, the introduction detailing the how and the why and the struggles stands as this incredibly vivid historical document. It captures the determination, the innovation, the birth pains of a whole new way of doing mathematics.
The formal arrival of computational number theory as a serious, rigorous field.
Absolutely. Before Haselgrove and Miller's work, large-scale, high-precision investigation of the zeta function's zeros was simply unthinkable. They didn't just calculate numbers, they forged the methodology. They established the standards for precision, for verification, for transparency that the entire field has built upon ever since. #outro.
Well, we have reached the end of our deep dive into this really quite remarkable, if unassuming, volume. Tables of the Riemann zeta function. We've seen the zeta function itself, why its complexity led to the need for that clever ZT shortcut.
We've navigated the, frankly, heroic challenges faced by the teams using the EDUC and the Manchester Mark, those early digital giants.
We wrestled with the absolute necessity of 15 decimal place precision, felt the pain of those emotional lows after discovering errors that wiped out weeks of work.
And we saw the payoff. The meticulous verification process involving Lamer, culminating in Table 3's list of the first 1600 zeros on the critical line, plus the tools like interpolation and the Riemann-Siegel formula needed to use and extend that data.
It really is this fascinating dual object, isn't it? On one hand, a technical data resource for experts. On the other, a historical monument marking the dawn of computational mathematics.
Absolutely. And ultimately, all that perseverance, all that computational horsepower harnessed for the first time, led back to understanding the deepest patterns in mathematics, the distribution of prime numbers, and even allowed them to overturn existing mathematical conjectures like Polya's.
Which brings us to a final thought for you. listening now.
Yeah, just consider again that immense effort. The teams of mathematicians and engineers, the room-sized fragile computers, months of computation, just to verify those first 1,600 zeros to 5 or 6 decimal places back in 1960. It was a major national-level scientific undertaking.
Now contrast that with today. Think about the device you might be listening on right now. The computing power you hold in your hand or sitting on your desk dwarfs those pioneering machines by orders of magnitude unimaginable back then.
Calculating those first 1,600 zeros to that precision today, it's trivial. It's a student exercise, computationally speaking.
So, if achieving that initial dataset of 1,600 points required such extraordinary determination and cutting-edge technology in its time, what does it say about the journey since?
What does it mean that we've now verified trillions of zeros, all lying perfectly on that critical line, using descendants of the very methods Hazelgrove and Miller painstakingly developed? The knowledge gap they bridged with this single volume wasn't just filled, it opened up an entirely new continent for mathematical exploration. They proved that machines could be partners in the deepest forms of pure mathematical discovery.
A revelation that continues today. Thank you for joining us on The Deep Dive.
See you next time.